This is the pre-lab for the first labs, which are the metric system and the density labs. So question 1, you, the student, will attend the lab intensive. Question 2, make sure to look at the lab manual. That's what these pre-labs are for, that students are familiar with the lab manual. So that's unit lab 1, measuring metric system, the objectives, you will find these 2 objectives. In the theory part for the same lab, you will find that physical quantity, number, and unit, all 3 must be written either separated with an equal sign or in tabular form. Conversion of units, sometimes needed within the metric system, usually not necessary between the metric and the US customer system, because we usually don't use this one except in the very first lab where I make a connection between the 2. Significant figures all the way through the semester and through this lab intensive must be adhered to. For example, a computer result may not look more accurate than the measured data. Measurement errors, experimental, random, and systematic ones. The random ones, we will always have them. We cannot minimize them. The systematic ones, we try to get rid of them. Sometimes we can. For example, we cannot get rid of friction. The experimental ones, that really refers to an experiment that is set up wrong. So we really want to get rid of the experimental ones. And then estimates. This is an important tool to assess the validity of a result. You may always want to have that in your mind that, hey, what do I expect? What's my estimate? Okay, conversion factors. Again, we really only need it in this particular lab because it's the only time that we're going to use American units. So kilograms to pound mass is 2 or 2.2 or 2.205, depending on the desired accuracy, and then so on. And you can match these up here. Notice that the order is in reverse. Okay, more on significant figures. Significant figures, when numbers are multiplied or divided, number of significant and final answer equals the smallest number of significant figures in any of the original factors. You come across that more often than not, and that one is true. And as you read through these here, they all should be true statements. Measurement errors, still the same lab. An experiment is set up incorrectly. For example, an electric circuit is not set up correctly. That renders any measurements meaningless. That's an experimental error. This one here is the same thing, experimental error. Systematic error. This one here, the experiment may be set up correctly, but you made a mistake in saying, hey, it's supposed to be 30, but instead it's actually 35. Then you will have a systematic error throughout. This one here also matches with systematic error. This one here measures with systematic error. I just mentioned it a couple of minutes ago that, for example, friction, you can't get rid of it, but it's still a systematic error. Then these here are random errors, so each measurement contains a measurement error that is restricted by the accuracy of the measurement instruments that are being used. For example, a caliper is measuring more accurately, or a stopwatch that measures to the closest tenth of a second. This error cannot be avoided. You can just minimize it. So all of these are random errors. Estimates. It's important to have a good idea of how large something may be before actually measuring it. That's true. You're not graded on the accuracy of your estimates. That's true. You should be able to make reasonable estimates using just one sig fig. That's what we usually do when we make an estimate. We're not going to go out and have like 4 sig fig attached to an estimate. So that's true as well. Your estimates must match your measurements exactly. Well, that's a contradiction to what I just said. No, they don't have to. These seem here in the reverse order. This is in the data analysis part, same lab. So make sure to look at the lab manual. Measure longer distance on foot. Pace, then convert your pace to meters. Measure your mass. Perhaps you only have access to a bathroom that shows pound mass, therefore convert to kilograms. Measure the size of a room. Use either metric measurement measuring tape or a metric ruler, and so on. Again, these should be in the reverse order. Okay, the other lab, for the density lab, these are the objectives, and the last 4 will apply. Again, look at the lab manual. That's the idea behind these pre-labs. And this one here is in the theory part. The density rho of a specimen is determined by measuring its mass and its volume. So rho equals mass divided by volume. The buoyant force exerted on a specimen equaling the weight of the displayed water is described by Archimedes' principle. And then you can read through these yourself, and you see there are a little turned around, these matching statements. Okay, this one here looks almost like every other one here with the ACEF. For the irregular shaped specimen, what are the equations? Well, again, look them up in the lab manual, and I posted that here. See the page on where it's actually posted. Why is the value for specific gravity equal to the value of the density? Because the specific gravity is defined through the density of water, which is in the metric system 1.00 grams per cubic centimeter. For cuboid-shaped specimen, what is the equation to determine its density? It's this one here, volume. Here is a typical density equation, but the volume is length times width times height. For a spherically shaped specimen, what is it? Well, it's still density equals mass divided by volume, but this time, of course, since it's a sphere, that's the equation for the volume of a sphere. This is for the density, still density lab. The procedures that you will find in the lab manual, make sure to look at the lab manual. And it looks like they're in the correct order. For the regular specimens, measure dimensions and mass, then compute the density. For the irregular specimens, measure mass and immersed or effective mass, and so on. If you set the container or beaker on a balance, on a scale, and so on, this here should be the matched statement. And again, you can read through this yourself. This is about the caliper, and there are several questions for the caliper. And they should be in the correct order, so look at these numbers carefully here. I'm just going to do one of them. The length of the steel bar is, well, how much it is. You look at where the 0 is. The 0 is between the 44 and the 45, so it should say 45 point something. And then you see which one is lined up the best of any one of these here. And it looks like the 4 is lined up the best. The 60 has no meaning here. It's just about the 4 itself. So you're going to have 44 over here, and then you have a 0.4 right there, which is what it says right here. This one over here, the 0 looks pretty close to being the 45 here, and if you see which ones are lined up among these here, you will see that it's actually the 0 that is lined up the best. So this one comes out to 45.0 millimeters. Should you write that 0 there? Yes, you do, because you are measuring that accurately. So if you leave out the 0 here and you just write 45, you're saying, hey, I didn't use the caliper, but you did. So you have to write that 0 there, because it tells us that you have measured that accurately. And again, you can look at these others here. Here I made an example form, but I just explained. This is where you get your first 2 digits, and then you see which one aligns, and that's where you get the next digit. Okay, there's another one here on the caliper. And here are the answers to that. These are not necessarily in the correct sequence, so there's the answer A, then there's B, E, and G answers. And that's it for the Unit 1 pre-labs.